Welcome back to my channel. This is part 9 of our Introduction to Calculus series, and today we're exploring integration. Let's get started. Let's start with this triangle, where the height is twice the base. What's its area? Easy. Use the formula for the area of a triangle. If the base is x and the height is 2x, then the area is x squared. Now try something harder. Calculate the area under this curve. This isn't as easy, right? One way to estimate the area is to divide the graph into several rectangles, calculate the area of each, and add them up. But the result isn't very accurate. If we make the rectangles narrower, the estimate improves. But it's still not exact. To get the exact area, we need the width of each rectangle to approach 0. Instead of using delta x, we use dx. And that's where integrals come in. They allow us to calculate the exact area under a curve. The symbol for an integral is this. Let's go back to the triangle's area. Notice that the slanted line is the function y equals 2x. So, to calculate the area under this line, which forms a triangle, we can use the integral of this function. See a pattern here? What's the derivative of x squared? Yes, it's 2x. That means integration is the reverse of differentiation. But pay attention. The result of an indefinite integral always includes a constant, written as c. Why? Because the derivative of any constant is 0. The derivative of x squared plus 2 is 2x. The derivative of x squared plus 20 is also 2x. The same goes for x squared plus 100, or any other constant added to x squared. That's why we always include plus c when writing the result of an indefinite integral. Let's look at a more familiar example. Imagine a car moving at a constant speed, for instance, 1 meter per second. To find the distance the car has traveled after t seconds, we calculate the area under the velocity time graph. Since the graph is a horizontal line, the area is simply a rectangle. Now, let's plot a graph showing the distance over time. We know the car travels 10 meters in 10 seconds, 20 meters in 20 seconds, and so on. So the graph is a straight line, representing the following function. What's the derivative of t? It's 1, which is the car's constant speed. Once again, this shows that integration and differentiation are opposites. The integral of velocity gives us distance. The derivative of distance gives us velocity. Let's now imagine the car is accelerating. Its speed increases over time. For example, suppose the velocity is given by this function. The velocity is no longer constant. It grows linearly. To find the distance traveled, we again calculate the area under the graph, which is a triangle. If we plot a graph of time versus distance, we see that the distance increases quadratically. Now, let's take the derivative of this function, which is exactly the velocity function we used earlier. But what about the constant c? Let's say the car didn't start from rest. Maybe it had already traveled 5 meters before we started measuring time. In that case, the total distance is the following, where, in this case, c is 5. So, this constant represents how far the car had already traveled before we started measuring. If we take the derivative, we'll always get the same result, because the derivative of a constant is 0. The constant doesn't affect the rate of change. It only shifts the graph vertically. What is the integral of cosine of x? It's sine plus c. This is straightforward, since the derivative of sine is cosine. This is called an indefinite integral, because it gives the full function, not just a specific value. But what if we only want the area between 0 and 90 degrees? To do that, we calculate the definite integral between those two values, or more precisely, between 0 and pi over 2 radians, since trigonometric integrals are always done in radians. To solve it, we subtract the values of the antiderivative at the limits. The constant c disappears in definite integrals, so the result is just 1. What if we want the integral from 0 to 135 degrees? That's the same as from 0 to 3 pi over 4 radians. Notice that from 0 to 90 degrees, the area is positive, and from 90 to 135 degrees, the area is negative because it's below the x-axis. If we just want the net result, we calculate the definite integral directly. But if we want the total area, we need to treat both parts as positive. That means calculating each area separately and adding them. But take attention. We want the absolute value in both areas, so we must revert the signal in the second integral. The total area is the following. So far, all the integrals we've seen are easy to solve. We just need to know the derivative and reverse the process to find the integral. Let's look at more basic examples, starting with the simplest one. The result is x, because the derivative of x is 1. We can generalize this to any constant a. Let's make things a bit more interesting. What's the integral of x? To solve this, we use the power rule for derivatives, but in reverse. The idea is to increase the exponent by 1 and then divide by the new exponent, because this derivative is x. We can apply the same rule for higher powers. Or, considering n different from -1, we can use this rule, called the power rule for integration. What happens when n is equal to -1? We can't use the power rule here, because the denominator would be 0. But if you remember the video about derivatives, this case shows up in one of them, specifically in the derivative of the logarithm of x. As I mentioned in that video, the full explanation is a bit too complex for this tutorial. So, once again, we'll just give the result. But why do we use the absolute value in the result of the integral? It has to do with the domain of the function. When we calculate the derivative of ln of x, we assume that x is greater than 0, because the log is not defined for 0 or negative values. However, when we calculate the integral of 1 over x, the only restriction is that x is different from 0, since it's in the denominator. To make sure the log is always defined in the result, we use the absolute value. This guarantees the argument of the log is always positive, regardless of whether x is positive or negative. Here are more examples of easy integrals, where we just reverse the derivative. For harder ones, we'll need to learn some integration rules first. And that's what we'll cover in the next video. And that concludes our lesson. If you've learned something new today, make sure to like the video and subscribe. I'll see you in the next video.